So cotilla test for pre-calc, if the cotangent is 3 over 2, the tangent's going to be 2 over 3. And then this is theta, so this is going to be my opposite side, this is going to be my adjacent side, and this side, the longest side, is my hypotenuse. So tangent is opposite over adjacent, so opposite over adjacent. It's going to give me a 2 there and a 3 there. And then I'm going to put that into my radical, which is 3 squared plus 2 squared. And that's going to equal the square root of 9 plus 4 equals the square root of 13. And I'm going to leave it as a radical. I'm not looking for a decimal. Sine is opposite over hypotenuse. That's going to give me 2 over root 13. And I'm going to leave it like that. I'm not going to rationalize it. I could rationalize it pretty quickly, but it's not necessary. Cosine is adjacent over hypotenuse, so that's going to give me 3 over root 13. Cosecant reciprocal function is going to be root 13 over 2. Root 13 for secant over 3. And that's it for number 1. Number 2, I have to graph this one. So I'm going to go left 3, up 2. And we have to remember the trig triangle. It's going to be that in quadrant 2. I go to the left negative 3, and I go up positive 2. My radical now to get my hypotenuse is going to be 2 squared. Plus negative 3 times negative 3 is the same as 3 squared. I'm still going to get radical 13. It's the same numbers as that one. But the negative gets canceled out when I square it. Whoops. Root 13 on the hypotenuse side. So, this side is now my opposite. This side is my adjacent. And the root 13 is my hypotenuse. Sine is opposite over hypotenuse, so it's going to be 2 over root 13. Cosine is going to be negative 3 over root 13. And tangent is going to be 2 over negative 3. And it doesn't matter where I place the negative, top or bottom or up front. Reciprocal identities, root 13 over 2. Root 13 over negative 3, but I'm going to put the negative on top. Negative 3 over 2. For number 3, I want to graph it. The amplitude is 2, so that means I'm going to go up 2 and put a dashed line as an upper bound. I'm going to go down 2 and put a dashed line as a lower bound. My period, I divide 2 pi by 1/2. That's going to give me 2 pi times 2 over 1, which is 4 pi. For me, just for my convenience, I like to always go out 8, 2, 4, 6, 8, and I place the period ending there. Half of 4 pi is 2 pi, half of 2 pi is pi, 1 pi, 2 pi, 3 pi. The sine graph is going to start, the cosine graph is going to start up high, and then it's going to go through there, and then go down low, go back up through, all the way up high, and I'm going to continue that every 2, that process. So I get this alternating pattern for the cosine graph. And when I actually graph it, I like to begin where at 0, 2, and then I'm going to connect the dots with a smooth curve. I always make the joke, I like my cosine and sine graphs like I like my women. Curvy. And there we go. Number 4, a secant curve. So the period, the amplitude is 1. That means I'm going to go up 1 and put a dashed line. I'm going to go down the negative 1 and put a dashed line, a lower bound. And my period is 2 pi divided by 1/4. I'm going to KFC it. That's going to give me 2 pi times 4 over 1. So my period is 8 pi. For my convenience, I like to go out 8, 2, 4, 6, 8. And I put my 8 pi there. Half of 8 pi is 4 pi. Half of 4 pi is 2 pi. 2 pi, 4 pi, 6 pi. 8 pi. I can't really graph secant. So the related function for secant is cosine. So I'm going to graph cosine x. And cosine starts up high, goes through, goes down low, goes through, goes up high, goes down, through, down below. I'm going to continue that pattern to get a nice array of points. So my cosine curve is going to look like this. But I'm not graphing cosine. I am supposed to be graphing secant. I'm not supposed to be graphing cosine. I'm supposed to be graphing the secant. In order to properly graph the secant curve, what I need to do now is notice that wherever it goes through the x-axis, I'm going to put a vertical asymptote. Wherever this cosine curve goes through the x-axis, I'm going to put a vertical asymptote. Wherever it goes through, I'm going to put a vertical asymptote. Wherever it goes through, I'm going to put a vertical asymptote. Again, wherever it goes through, I'm going to put a vertical asymptote. Now, my actual secant curve is going to look like this. It touches at that high point and then goes up to infinity. It touches at that low point and then goes down to negative infinity on both sides. Touches at that maximum, which is actually a minimum on the secant curve. The maximum on the cosine curve is a minimum on the secant curve. Nice to know if you are applying this in calculus. That's nice to know. And there it is. That's my secant curve. I can cheat over that way a little bit. Solving trig equations, I could either factor this or solve it by using the square root method. The vote today was we solve it by using the square root method, so I'm going to do 16 sine squared x, add 4 to both sides, equals 4. Then I'm going to divide both sides by 16. This is going to give me sine squared x equals 4 over 16, which is the same as 1/4. And now the opposite of squaring is square rooting. When you add the square root, you add a plus minus. The square root of 1 is 1. The square root of 4 is 2, but don't forget, it's plus minus. Now what I'd like to do is go to my sine chart, or my unit circle chart, and I'm looking for wherever sine equals positive or negative 1/2. Sine equals positive 1/2 at 30 degrees, positive 1/2 at 150 degrees, negative 1/2 at 210 degrees. And way over here to the right, negative 1/2 at 330 degrees. So there are my 4 answers. Notice I have 4 answer spots. Sometimes I make a mistake and put too few or too many, but in this case, I did it just right. 30 degrees, 150 degrees, 210 degrees, 330 degrees. The next one, I'm going to cover this up and add 2 root 3 to both sides. So it's going to give me 3 cosecant x equals 2 root 3. I'm going to divide both sides by 3. Now I'm going to look at my sine chart for where cosecant x equals 2 root 3. Only positive 2 root 3. I repeat, I did not have to square root both sides. So I'm looking for where cosecant equals positive 2 root 3. Let's see if we can't find that. Cosecant equals positive 2 root 3 over here at 60 degrees, positive 2 root 3 at 120 degrees. So we're going to write that down. 60 degrees and 120. For the next one, I'm going to solve it again by using the square root method. I'm going to add 12 to both sides, so it's 4 tan squared x equals 12. Divide both sides by 4. This is going to give me tan squared x equals 3. Now, the opposite of squaring is square rooting, so I'm going to square root both sides. When you add the square root, you add the plus minus. So now on my sign chart for my unit circle, I'm going to look for where tan x equals either positive or negative square root 3. Let's see if we can't find that on the table. So now I'm looking for tan x is positive or negative root 3. Tan x equals positive root 3 at 60 degrees, negative root 3 at 120 degrees, positive root 3 again at 240 degrees, and negative root 3 at 300 degrees. So we're going to write those down. 60, 120, 240, 60, 120, 240, 60 degrees, 120 degrees, 240 degrees, and 300 degrees. All 4 slots are filled in. This one looks like it's going to be kind of daunting. Number 8 is a little harrowing. I'm going to implement ZPP. I'm going to set each of these quantities equal to 0. So secant squared minus 4 equals 0. And I'm also going to set secant squared, supposed to put an x in there, x minus 1 equals 0. I'm going to simultaneously solve both of these using the zero product property. So I'm going to add 4 to both sides. That's going to give me secant squared x equals 4. Square root both sides. That's going to give me secant x equals plus or minus 2. I have to look on my unit circle table to find that. I will do that eventually. Now I'm going to solve this one, secant squared minus 1. So this is going to give me secant squared x equals 1. I square root both sides. When you add the square root, you add the plus minus. So I'm looking also where secant x equals plus or minus 1. I think I made a mistake on this for the answers. I have 2 items too many. So now I'm going to look on my table. So where secant equals plus or minus 2, where secant equals plus or minus 1. Secant equals plus or minus 2, secant equals plus or minus 2 or plus or minus 1. So there's a 1, secant equals 1. There's a 2, secant equals 2. There's a negative 2, secant equals negative 2. There's a negative 1, secant equals negative 1, negative 2, and positive 2. That's going to be at values of 0 degrees, 60 degrees, 120, 180, 240, and 300. If you have this table, the answers work out rapidly. So my answers are going to be 0 degrees, 60 degrees, 120 degrees, 0 degrees, 60 degrees, 120, 120 degrees, 180 degrees, 240 degrees, 300 degrees, and that's it. For number 9 and 10, I want to convert the radians and convert the degrees. For this one, to convert the radians, I'm going to multiply 540 by pi over 180. Notice the zeros will cancel, and then 18 goes into 54 3 times, so my radian value is 3 pi. To convert pi over 2 degrees, I can either go to my unit circle, then notice that at pi over 2, the degree value is 90 degrees, or I can multiply it by 180 over pi. So pi over 2 times 180 over pi. Notice the pi's will simplify, and 180 divided by 2 is 90 degrees. Radians, degrees. Using the difference quotient, most of us are getting pretty good, pretty confident at the difference quotient. First thing I'd like to do is put this f of x behind the minus sign, x squared plus 2x minus 13. We must remember to quantify it or put parentheses because we have to distribute that negative a little later. Now, up front, wherever there's an x, I'm going to put a quantity. Wherever there's an x plus 2x, I'm going to put a quantity. Minus 13, there's no x there. Inside the x, I'm going to put x plus h. Where inside the x, I'm going to place the x plus h. And now I have some petty algebra to do, and I'm going to do it. First, I'm going to FOIL out x plus h. X plus h squared is x squared plus 2hx plus h squared. I did that. Now I'm going to distribute the 2 plus 2x plus 2h. Nothing to do with the negative 13, so I'm just going to copy it down. Now I'm going to distribute the negative. That's negative x squared minus 2x plus 13. Now, once you get experience at doing difference quotient, you'll notice everything from the tail end simplifies with stuff up front. So let's see what happens here. The positive 13 is going to simplify with negative 13. The negative 2x is going to simplify with the positive 2x. And the negative x squared is going to simplify with the positive x squared. Now, that's only going to leave me a couple items. 2hx plus h squared plus 2h. I can factor an h out of that. That's going to give me h times 2x plus h plus 2 all over h. Notice the h is simplified, and this is going to equal just 2x plus h plus 2 as my final answer. Now I'm going to find the derivative. This is a typo. It shouldn't be f prime. It should just be f. The derivative using the general power rule, I do 2 times 6, so that's going to give me 12x, and then I subtract 1 from that, so it's 12x. The derivative of 3x is just 3, and that's it. So I can put f prime of x equals that. That means derivative. Little note for number 13, secant, tan. The derivative of tangent is secant, or secant squared. That's a helpful note. So again, f prime, or the derivative, equals secant squared. The derivative of sine x is just cosine x. That's something most of us just try to commit to memory. Now I'm going to do the product rule. I'm going to crack this in half like an egg. I'm going to place a u on the left, a v on the right. So, u equals 2x cubed. V equals sine x. The derivative of 2x cubed, power rule is 3 times 2 is 6x minus 1 squared. The derivative of sine x we already figured out is cosine x. And now I'm going to follow my little pattern, u dv. So u times dv is going to give me 2x cubed cosine x plus v du. Sine x times 6x squared. But in calculus, we usually put the polynomial first. 6x squared sine x. Quick graph, number 16. This is y equals mx plus b. I begin at positive 3. And and my slope is 2 over 1. So I go up 2 over 1 and I run out of room. So I need to continue that pattern going in the other direction so that it's a linear. It's a line. So here's my graph of y equals 2x plus 3. Y equals 2x plus 0. This is mx plus b. I begin at 0. And I continue to go up 2 over 1, up 2 over 1. Notice it's going to follow that same array going in the opposite direction. So that's y equals 2x. It goes to 0, 0. Y equals 2. This is a vux or a hoy. In this case, it's a hoy. A horizontal line through y equals 2. So I go to y equals 2, and I'm going to graph a horizontal line through y equals 2. And the slope of that line is 0. X equals 4. This is a vux. That means it's a vertical line through x equals 4. That's a line that goes straight up and down. The slope of that line is undefined. That's what the u means, undefined. This is a parabola whose center is located at opposite sides. Another parabola, this time it's concave down, but its vertex is located at positive 1, positive 5. So I go right 1, up 5. I'm going to implement 1, 3, 5 again, but notice this time there's a negative 2 out in front. So I'm going to multiply those numbers by negative 2. So it gives me negative 2, negative 6, negative 10. So from that vertex, I'm going to go down 2, right 2, down 6. 1, 2, 3, 4, 5, 6, right 1. And now I ran out of room. So I'm going to go down 2, left 1, down 6, left 1. Whoops, I missed it. This is going to give me a nice parabola, concave down with a maximum, and it's got a vertical stretch because a is greater than 1, absolute value. This is a cubic. It doesn't have a vertex. It has a turning point at negative 1, negative 1. So I go left 1, down 1. I place my turning point. Cubic uses 1, 7, 19. So I go up 1 over 1. Now I'm supposed to go up 7 over 1, but I don't have enough room. I go down 1 over 1. Then I'm supposed to go down 7 over 1, but I don't have enough room. So I'm just going to fake it and creep it up. And there is the graph of the cubic. This is the cubic whose turning point is at 0, 0. So I go up 1, right 1, down 1, left 1. And this one, again, I'm going to fake it. I'm just going to creep it up like this. This is a radical function. It's got a turning point or a starting point at opposite same, negative 4, negative 3. So I go left 4, down 3. The array of points for this is 1, 3, 5 as well, but I go up 1, right 1, but then I go up 1, right 3. Instead of going in a parabolic, it's a radical shape. So I go up 1, right 5, and then my curve starts at that coordinate and then out routes to the right. For number 25, again, another radical function, but this time the vertex is located at 0, 2. Notice there's nothing in with the grouping. So I start at 0 and I go up 2, and that's my starting point. And I'm going to implement the 1, 3, 5 again. From there I go up 1 over 1, up 1 over 1, 2, 3, and I run out of room. So I'm just going to go ahead and sketch my curve. Absolute value is a v. And this v has a vertex at negative 1, negative 5. Opposite same, so I go left 1, down 5. The slope in front is 1 over 1. So I go up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. Continue that. Now absolute value is a v. So I continue this in a v shape on the left side of the vertex. Last one is a cubic. A cube root though. It has a turning point at opposite same, negative 1, negative 2. So I go left 1 and I go down 2. 179 is the array of points, 1719 is the array of points for a cubic and a cube, but that's going to run out of room really quick. So I go up 1 over 1, I go down 1 over 1, but now I'm supposed to go up 1 over 7, which is going to land me way over there. I'm just going to fake it and get an idea of what the curve looks like. It creeps over that way. It's a super S.